Kia ora koutou, no mai, haere mai. Welcome to lesson 9 for introductory physics. In the previous couple of lessons, we've looked at forces, talked about what they are, their vectors that represent pushes or pulls, and then we looked at Newton's 3 laws, which sort of formalize some of those hopefully fairly intuitive ideas we have about forces. This lesson is going to step back again, rather than looking at the laws and exactly what forces do. We're going to look at where forces come from in terms of the different types of forces that we see in common problems. So that's the goal today. There will of course be far more types of forces than we see right here, but we're just going to have a look at a few of the common ones. So the goal is obviously to learn a few different types. We've got forces due to gravity, given by the universal law of gravitation. We've got the normal force, which is also called the support force occasionally. We've got friction force, and that will lead us into discussing terminal velocity as well, which is a little side step there. And then we've got a tension force, and finally we're going to look at Hooke's law, which involves springs. So part 1, gravity. The universal law of gravitation, sorry, wrong way around, the law of universal gravitation is that everything in the universe pulls on every other thing. All matter attracts all other matter. It's quite a weak force compared to many other forces that we see, especially when we get later in the course, we're going to meet electrical and nuclear forces. Those are much stronger, so gravity is quite weak compared to those. It also means that we don't notice it for most objects unless one of them is really big. You'll see what I mean with the next formula. The formula that tells us the strength of this force is this one right here. We've got F equals G times M1, M2, so that's the masses of the two objects, divided by D squared, which is the distance between the objects squared. And that big capital G is the gravitational constant. You can see that's given just below the formula as 6.67 times 10 to the negative 11 newtons meter square per kilogram square. So that times 10 to the negative 11 means that that G, that big capital G, the constant, is really, really small. It's a 6, or rounds to a 7 in the 11th decimal place. So that means the only way that this force gets noticeable is if at least one of those two masses are really, really big, or the distance between them is really, really small. And it turns out you can't really get that small. We'll learn more about the distance that objects can get together in I was about to say which lesson number, but I don't want to guess. So it's in the second half of the course when we look at what matter is made of. So this force is small unless one of the masses is really big, like a planet or a moon. The direction of the force is directly towards the center of mass of the other object. So we haven't met center of mass yet. We'll do that in a couple of lessons, but we have a magnitude given by that formula and a direction directly towards the other object. On Earth, if you take a 10 kilogram object and you use the mass of the Earth as 5.97 times 10 to the 24 kilograms, which is approximately correct, and the radius of the Earth as 6.37 times 10 to the 6 meters, again, that's about right. The Earth isn't a perfect sphere, but it's pretty close. So we'll take that as the radius. And if you put those numbers in, you get a force on a 10 kilogram object of 98.1 newtons. And this force is called the object's weight. Weight always points towards the center of the Earth. It's a force, so it is a vector. We don't usually bother specifying the direction for that reason. The direction of the weight force is what determines up and down in our everyday language. That's how we know what down is. It's the direction that things are attracted due to the gravitational attraction with Earth. That's what defines up and down. So we don't normally bother specifying the direction of something's weight force. We know that that is straight down towards the Earth's center. And if our frame of reference happens to have up and down as one of our axes, then we know that it's going to be down in that axis. If not, we still know that it's down relative to the Earth's surface. And if we have a different frame of reference, then we need to convert that downwards in Earth's surface to our other frame of reference. The acceleration of that 10 kilogram object we can determine using Newton's second law, because we know that F equals ma. If we have a net force, so this is assuming we've got no other forces on this object. So imagine there's no air resistance, imagine there's nothing in the way. and somebody lets this 10 kilogram object go, it starts accelerating towards Earth. Newton's second law tells us that A will be equal to F over m. We've just calculated F. We divide it by the mass of the object, which we said was 10 kilograms. That gives us an acceleration of 9.81 meters per second. And that's the acceleration due to gravity that we already expected. So that all seems to work out. Indeed, if we take any object on Earth and we leave that, the mass is an unknown. So we just leave it in our formula as m with a little subscript O for object to make sure we're talking about the object mass, not the Earth mass. And we put in the rest of the numbers into that equation. What we see is that the force is equal to 6.67 times 10 to the negative 11 times the mass of Earth, 5.97 times 10 to the 24, divided by the distance from the object to the Earth's center, which is pretty much the radius of the Earth because we're assuming it's near the Earth's surface, divided by that distance squared. That gives us 9.81 times m0 newtons. That's how much the weight force is, the magnitude of the weight force is for this object, any object of mass m0. And therefore the acceleration is going to be that, that magnitude weight force divided by that mass of the object. And since we've still got MO in our value, it's not 9.81 newtons, it's 9.81 times MO newtons. We've still got MO in there, so we just cancel out the MO and we're left with the acceleration always being 9.81 meters per second. So the point of gravity, not the point, what we see with gravity is that bigger objects, bigger mass objects do experience a greater weight force, but because the acceleration due to Newton's second law is proportional or inversely proportional to the mass of the object, that mass actually cancels out in terms of our final calculation, and every object experiences the same acceleration, again, assuming there are no other forces involved. So when this gravitational force involves any object and any planet or moon, then we refer to it as the object's weight. That means we can talk about something's weight on the moon or on Mars, and it'll be different to its object, that object's weight here on Earth. If we don't specify the location, if we just say an object's weight in our scenario and we don't specify where it is, then we assume it's talking about weight on Earth. So weight on Earth is the default. If you are talking about the weight in a different location, then you need to specify that. It's always directed towards the center of the planet or the moon involved. Just to recap, mass and weight. Mass is simply a quantity, it's a scalar, it's how much of something we have. In the same way that you can say we have 2 apples or 4 apples, and that is just a scalar, it's not a vector, there's no direction, it's just a quantity. And you can also say that you've got 2 kilograms of something or 4 kilograms of something or however many kilograms of something. It's just a quantity. There's no direction involved. It's just how much of it do you have. Whereas weight is the force due to the gravitational attraction between an object and the planet or moon that it is nearby. Just as a little aside, this isn't particularly important, but if you've ever wondered why Earth and other planets and the moon are spherical, it's because of this universal law of gravitation. When we do problems involving a planet or a moon and an object, we treat the planet or moon as a single big object with a huge mass, but in reality, of course, it's made up of lots of small parts, and all those parts are attracted to all the other parts. And it turns out that when everything is attracted to everything else in some big group, the natural shape that it will form is a sphere because it's all trying to get as close as it can to itself. And that means it forms up into a ball. That's why if there was a big pointy bit, the Earth would just pull it flat. And indeed, that's exactly what happened when planets are forming. When planets are forming, all the bits and pieces that they're made of all just sort of pull into each other and they form into this big ball. So they do start all separated, all pulled out, and then pull into a nice compact sphere. A common question then is, why do we have mountains? Why is there height differential as you travel around the world if it's trying to be a perfect sphere? The answer is that there's not really much of a height differential. The Earth's radius is about 6,370 kilometers. That's just the radius. So from the center of the Earth up to the surface, about where you are, is around about 6,370 kilometers. The tallest mountain on Earth is less than 9 kilometers tall. Less than 9 kilometers versus over 6,000 kilometers. It's about 0.14% of the radius of Earth. So it's actually really, really small height differentials between the tallest points on Earth and the lowest points on Earth in terms of those surface heights from the center of the Earth. Very tiny differences. Just that small text there is just to put it in perspective if you want to visualize that in a different way. Imagine a basketball. They have radiuses of around about 24.3 centimeters. If the Earth were that size, then the tallest mountain would be 0.032 centimeters, or about 1/3 of a millimeter tall. So the variation in this height of that surface of the Earth, if it was the size of a basketball, is about 1/3 of a millimeter. So it's done a pretty good job of turning the Earth into a perfect sphere. Second part, normal force. If there was nothing between you and the center of the Earth, you would just continue accelerating all the way towards the center until you reached it. That's what you would do if there was nothing in the way. Obviously, the Earth itself is in the way, and other objects can be in the way, the floor, chair, plane, hot air balloon, whatever happens to be in your way. So that means that you can't just keep accelerating towards the Earth, but you will push on the thing that's in the way. The thing that's in the way is going to push back on you. That's Newton's third law. You push on something, it pushes back. You're pushing on it because gravity is pulling you down. Therefore, this object, whatever's in your way, is going to push back on you. And that's called the normal force. As I've mentioned, sometimes people call it a support force. I prefer to call it normal force, and we're going to talk about why. The normal force from a surface is always perpendicular to the surface. Perpendicular just means at right angles. And in a mathematical sense, the word normal means at right angles to, or perpendicular to. If you have a frictionless surface, then the only way the object will stay perfectly at rest is if the surface is perfectly horizontal, so that the object doesn't slide one way or the other. If that surface is even slightly on a slope, that object is going to slide down the slope. Right? That's what down means. It's the way the object is going to go due to gravity. So if the slope does have a downwards direction, the object will slide down it. So that surface has to be perfectly horizontal if it is frictionless. And then the normal force would be perfectly vertical, and thus it would cancel out the weight force. So that's the only way that the normal and the weight force would cancel, is if they're perfectly equal and opposite. So here's an example. On a horizontal surface, we've got the weight force on the object straight down and the normal force on the object straight up. Notice that these are both forces acting on the object. The object is our system here. The surface is not part of a system. If we were going to include the surface in our system, we would have to illustrate the force of the object pushing onto that surface. And that's not the weight force. The weight force acts on the object and pulls it downwards. But because of that weight force, because it's being pulled downwards, it pushes onto the surface. So it's a push force, effectively. It's the object pushing onto the surface. The surface then pushes back with the normal force. And so that push force, which is due to the weight force, but it's not the weight force, that push force down on the surface and the normal force back up onto the object, those are the pair of forces that we can identify by Newton's third law. But the weight force and the normal force do both apply to the object. That means we can cancel them out, and we have no net force, and the object is in equilibrium. So if that surface is perfectly horizontal and the object is not moving and there's no other forces involved, then the normal force and the weight force will always be equal and opposite. They will always be equal and opposite, and that will keep the object at rest sitting on that surface. However, when we've got a sloped surface, we can't just make that same assumption that the normal force is equal and opposite to the weight force, because indeed it won't be. Remember that the normal force is always perpendicular to the surface. That means if our slope is angled down to the right like it is here, then that means that the normal force is going to be perpendicular away from that surface. It will be up and to the right. You can see that normal force there as the red arrow is now pointing at an angle. The weight force, of course, is still directly downwards. The weight force is still straight to the center of the Earth. That means the forces cannot cancel out. If they're pointing in different directions, there's no way they can cancel out. They can partially cancel, and so we end up with a net force that is pretty small compared to either of the two original forces, the weight force and the normal force, but they will not completely cancel out. That means we will end up with a net force, and intuitively you'd expect the net force to be in the direction of the slope, because if that object is going to move, the only way that makes sense is that it will accelerate down the slope. It wouldn't make sense for it to fly up off the slope or travel into the slope. That's not possible. So it will accelerate down the slope. So we already know the direction that it's going to move in. Weight is the most common cause of a normal force, but it's not required. If you put a box on the ground and you push it until it hits a wall, and then you keep pushing it, you are pushing against that box, and that box is then going to push against the wall. That wall is going to provide a normal force back to the box. So now weight isn't the only way to get a normal force. So in the case of the box, it's sitting on the floor and you're pushing it into a wall, it's going to experience two normal forces, one from the floor upwards, one from the wall back towards you. It's also got two other forces, the weight force downwards and the force from you into the wall or towards the wall. That means that overall it can be at net zero force, but it's still got two normal forces. So do keep in mind that normal force is simply the result of any object being pushed into a surface and that surface not letting it move. Usually the force that's pushing it into the surface is going to be the weight force, the gravitational attraction of the planet or moon that it's on, but it doesn't have to be. In the same way that you can't push the box into the wall, the object, no object can get to the center of Earth. That's what we said at the start. The Earth is in the way. Right? That means that the force that is trying to move the object is effectively being passed on by the object to whatever is in its way. That's what that's why we get a normal force. We're pushing on the ground and the ground pushes back up on us. Sometimes weight is used to refer to this downwards force exerted by an object onto the surface that's supporting it. So that means that rather than talking about the gravitational force that's attracting an object to the Earth, sometimes people, when they say weight, they mean the force that an object exerts onto the surface in its way, the one that's preventing it from moving in a direction it's being pushed or pulled. Now there's nothing specifically wrong with that. It's not the way we just defined weight, so I won't tend to use it in this manner usually. However, there are some scenarios where we do. But first of all, let's think about what happens if we do use that alternative definition. So if we are talking about the weight force being the force that an object exerts onto a surface, so that push force effectively of an object onto a surface, and then you start to think about some scenarios that involve moving surfaces, like standing in an elevator. If you stand in an elevator and the elevator accelerates you upwards, then for you to be accelerating upwards, you must have a net force upwards. There are only two things interacting with you when you're standing in an elevator. You've got the gravitational force with Earth, and you've got the normal force from the elevator floor. That's it. That's all that's interacting with you, the elevator floor and the Earth. If you have a net force upwards, then that means that the force on you from the elevator floor must be greater than the weight force due to Earth's gravitational attraction. By Newton's third law, we know that the force that you exert down on the floor of the elevator is the same as the force that the elevator exerts back up onto you. That means that your weight, the force you're exerting on the floor, is greater than the gravitational force of attraction with Earth. Right, so if you define weight in this way, as the force you exert on the surface that's in your way, then you gain weight as you get accelerated upwards. Conversely, you lose weight as you accelerate downwards. So if you are accelerating downwards, then your net force is downwards. That means the force that is being exerted on you by the elevator floor is less than the force being exerted on you by gravity, and your weight would therefore be less. The elevator in that sense doesn't force you downwards, it just controls how quickly you fall due to gravity. Right? It's not really providing a downwards force on you, it's letting gravity be a bigger downwards force. So in that sense, if we define weight that way, and then the elevator started to accelerate downwards at 9.8 meters per second, or equal to the acceleration that you would experience naturally due to gravity, you would have no support force at all. You would just have the force due to gravitational attraction with Earth, and you would have no support force, and therefore you would have no weight with this alternative definition. You would be in free fall. So in that sense, if you call something weightless when they have no support force, then move up to the ISS, the International Space Station. Think about what's going on there. We already talked about them when we talked about projectile motion, and we said that they are actually just in constant free fall. If they're in constant free fall, what that means is that the ISS, the room that they're in, the area that they're in, is just always accelerating at the same rate that they are. And if it's accelerating at the same rate that they are, then it's not going to provide a support force. And that's exactly what's happening. So the astronauts on the ISS do still have a weight in the sense of a gravitational attraction with Earth. We already talked about that. It's not quite as strong as it is on Earth's surface, but it's still there. But they're not getting any kind of support force. So when we talk about being weightless in a space station, we're not talking about having no weight force due to gravity. We're talking about having no support force and thus not exerting any force on the surface in your way. So we do actually use this alternative definition of weight all the time when we're talking about astronauts and weightlessness up in space. So we've now seen several different uses of the word weight. We've got everyday language where weight means the same thing as mass in kilograms if we're talking scientifically. We've got the weight force due to gravity, which is the gravitational attraction of an object and a planet towards each other, and the force exerted by an object onto the surface that is supporting it. So we've got these three different definitions, and therefore it's especially important to be vigilant about what you're talking about when you talk about weight force. Right? So do be careful about that word. As I said, occasionally we'll talk about other planets or the moon. This is just a reminder that if we don't specify the location, you can assume it is on Earth. If we say an object's weight is 10 newtons, then you can assume it's on Earth and therefore figure out its mass. But if we say its weight force is 10 Newton on Mars, then you can't determine its mass from the same formula we would normally use of dividing by 9.81 because we don't know what the acceleration is on Mars. The next part is friction. Friction is a very common force, but it's also one that we sometimes just deliberately ignore while we're solving a problem to try and make it simpler. So a friction force is a force that opposes the relative movement of two objects due to that relative motion. It occurs, if it occurs, it is always in opposite direction to the velocity of the moving object. So if something is moving in some direction, sliding along a surface or being pushed along a surface, then if there is friction, it will be directly opposing the velocity. It will always oppose the velocity. Remember that velocity is a vector, it's got a direction. The friction force is a force, so it's a vector and it's got a direction, and that direction is going to be exactly opposite to the velocity. Most people already have an intuitive idea of friction, the idea of two surfaces rubbing against each other and sort of preventing each other from moving somehow. And that is often true, that's often the cause of friction. And it's because surfaces are not smooth. If you look at a surface at a microscopic level, even what appear to be smooth surfaces are actually quite rough and irregular. The top image is a piece of silver metal after being chemically cleaned. So that's a cleaned, smooth surface of metal, and you can see that it's still got some sort of grains and pitting in it. It's not a perfectly smooth surface. It's pretty good, but it's still not perfectly smooth. The bottom image is a wooden surface, and wooden surface, wood being part of an organism, part of a tree that's been cut and treated and processed. Again, you can get them smooth, you can sand them down, you can polish them and fill in some of those gaps. You can make them smooth, but naturally wood is pretty rough. So these surfaces are not smooth. And if you try and push them past each other, then the rougher and bumpier they are, the harder time they're going to have actually moving past each other, because at that microscopic level, the interaction between those two surfaces means that you've got bumps trying to get past bumps. So when those bumps are trying to get past other bumps, you have to either deform the object, you either have to actually physically push part of the object out of the way, bend it or break it over, or you have to lift up the top object or separate the two objects slightly to let that bump past. And that's all friction is. Friction is just the force needed to deform that object. We'll talk more about deformation later, but we won't really go into detail on friction deformation. But you either need to deform that object, push the little bumps out of the way and effectively smooth the surface out a bit as you're moving, or you need to lift up that object. That means opposing the weight force, lift the object up so it can get over the bump. So either way, that's going to take a fair bit of force. right, depending on how much friction there is. How much friction there is what we determine, state as the coefficient of friction. And you'll notice the letter for this, the symbol, is a little mu. It's a Greek letter. It's not the letter U. It's called mu, M-U, mu. And it looks like a U, but with a little tail at the start. So we've got this little thing out the front of the letter. And that is just a number that tells us how much friction will occur with two objects of different materials. There's no way for us to theoretically calculate this in most cases. What we have to do is just find out what the materials are that are involved and then look up the coefficient of friction for those two materials when they're rubbing against each other. That's the best we can do, is to get a whole big bunch of reference tables full of experimental data from people that have done these sorts of things in the past and figured out their friction force, and use that to figure out how much friction we're hopefully going to see in a new scenario, a new problem. It depends on the materials of both objects involved, because obviously even if you've got a rough object sitting on a really smooth one, even if the really rough one is really rough, if the surface that it's on is really, really smooth at a microscopic level, you're not going to have any problems with the roughness of the first one. So even one being smooth can be a big advantage. If they're both really rough, then obviously it's going to be even worse. So it depends on both of the materials. So when you look up a coefficient of friction, you need to look up for the pair of materials that are involved. Here's some examples: ice and steel. So ice is a nice smooth version. In reality, ice is generally low friction because the top layer starts to melt and you actually get a little layer of water which sort of fills in any gaps naturally. So that's why ice is often a pretty smooth, frictionless surface. And steel, being a nice smoothed processed metal, we can make it fairly smooth as well. And so you get a very low coefficient of friction. 0.03 is our coefficient. There are no units for the coefficient of friction. We'll talk about why shortly. Diamond on diamond. Diamond is a nice, hard, solid structure, but it's also very geometric in its shape, which we'll talk about the structure of atoms and molecules at the level of making up matter in the second half of the course. So it's also got a low coefficient of friction. When you get to a wet tire and a wet road, what I was just saying about water naturally filling in the gaps, that happens on the roads as well. And that is why you have a low coefficient of friction in the rain. Brass and steel, to hopefully smoothed, these are assuming smoothed out bits of metal, not just a natural lump of ore, but processed human-made pieces of metal. 0.35, brick and wood. So wood and brick are both relatively rough. We're getting up to 0.6. Rubber and asphalt. So this is a tire on a road in sort of normalish conditions is going to be 0.9. And by the time you get to a dry tire and dry road, you're getting up to about 1. So that's ideal compared to wet tire and wet road, which we saw was 0.2. And if you actually just have pure rubber on pure rubber, then you get a friction coefficient all the way up of 1.16. So what does this coefficient of friction mean? The heavier the object is, the more it pushes down on the surface it's on. And that's what we've said. It takes that weight force and it sort of effectively passes it onto the surface. It says, I want to move downwards, but I can't, you're in my way, I'm going to push down on you. That surface then pushes back up with a normal force. If you've got a heavier object, it's going to push down more, and those bumps are going to be more pushed into each other, more smushed up together, and harder to then get past each other. And if you want to get the whole object up and over a bump, then that's a lot more force needed because the whole object is heavier and you have to lift it up a bit more and so on. So the heavier the object is, then the more friction you're going to get. So that coefficient of friction tells us about the interaction of the two surfaces, but we still need to account for this weight somehow. The bigger weight force is going to have bigger friction. And it turns out that the maximum friction two objects can have, or an object on a surface can have, is equal to that coefficient of friction, mu, times the normal force, F sub n, the normal force. Notice that it's not the weight force, because it's not actually how much the object is being pulled straight downwards, because what if the surface is vertical and the object is just being pushed up against it? Now the weight force isn't relevant. All that is relevant is how much you're pushing the object against the wall. So imagine there's a wall, I push a box up against it. there's friction now between the box and the wall, but that friction, how much there is, depends on how hard I push the box into the wall. It has nothing to do with weight anymore. So the weight force isn't actually relevant to our friction force, but it may indirectly be responsible for the size of the normal force in a perfectly horizontal scenario. So the maximum friction force is mu times the normal force. But this is the maximum. It's the maximum that can occur, but it doesn't always occur. It doesn't always occur because remember that friction is a response to relative velocity. If you've got a really, really heavy object sitting on a horizontal surface, it's got a really big normal force, and the friction coefficient, even if it was a really big rubber object on a really big rubber surface, the friction coefficient is big, so we've got a big maximum friction force that can occur. But if the object is at rest, there's no friction at all because there's no velocity. And it's only when you've got velocity that you are going to have friction. Sorry, I should clarify. It's only when you've got something attempting to give the object some velocity. There's not always going to be velocity. Hopefully that's not too confusing, but let's continue thinking about it a little bit more. How much actual friction do we get? Well, normal force is perpendicular to the surface and friction force is parallel to the surface. To know how much actual friction force is being experienced, the best approach is to decompose all your forces into the frame of reference aligned to the surface. So this is why choosing our own frame of reference is very important. When you have a sloped surface like this box on a slope, then putting everything into the frame of reference means that we now have the normal force in our y direction and the friction force in our x direction. Because if those two objects, if that object is going to move along the surface, it will move up or down the x direction, and the velocity would therefore be up or down the x direction, and the friction force would then be the opposite. So the friction force would only be in that x direction. What that means is we have to decompose our weight force, because our weight force is vertical in terms of the Earth's frame of reference. If we want to use this angled frame, then we can decompose it into a y and an x component within our new frame of reference, our angled frame of reference. So you can see I've done that there. I've just that's just vector analysis. If you know the angle of the slope, you know the angle of that. Well, there is a worked example of this in the next lesson if you're getting concerned about that approach. The normal force will be equal and opposite to the component of the weight force in that y direction, in that y dimension that we've chosen for our frame of reference. Sometimes we just call it parallel and perpendicular rather than x and y, just to remind ourselves that x is parallel and y is perpendicular to the surface. So normal force is perpendicular to the surface. That's how normal force is defined. And the weight force in that dimension that we've found, that direction that we've found, is going to be equal and opposite. We know they're going to be equal and opposite because we know the object isn't going to fly up off the surface. That means we have this component of the weight force in the parallel direction that hasn't been cancelled out. So that's our net force if we had no friction. That's what we saw in the just before when we were talking about normal forces. So if we have that much force trying to make the object go down the slope, but the object doesn't go down the slope, then the only thing that could be stopping it would be friction. So the friction would just be enough to stop the object sliding down the slope. If the object has a net force down the slope, it will accelerate down the slope. If it remains at rest, it can't have a net force. Therefore, the friction force must be the one that's cancelling out that parallel component of the weight force. And that's how we actually figure it out for an object at rest. So as I said, friction is a result of the relative motion of two objects, but it can also be the result of attempted relative motion between two objects. If there was no force trying to push an object along the surface, so in our perfectly horizontal system, a perfectly horizontal surface with an object sitting on top of it, there's no force trying to make that object move sideways. So there will be no friction force. The required force, if it's less than the maximum, then it will just be enough friction to stop it moving, right? It's not going to take the maximum friction force, because if the friction force was maximum, we'd now have a net force up the slope and the object would just spontaneously travel up the slope, and that obviously makes no sense. So that means that you can only have enough friction force to oppose the force that's trying to cause motion. If, on the other hand, the maximum friction force is less than what would be needed to oppose the motion completely and keep the object at rest, then that means that it will just take the maximum. You can't get more than the maximum, obviously, so the object would only experience the maximum friction, and it would then have a net force down the slope because there's not enough friction to cancel out that downwards, that parallel component of the weight force. Technically, when two objects are moving, then the static coefficient of friction is not going to be the same as the friction coefficient while the object is moving. What I've been talking about so far has been static coefficient of friction, but I'm not going to go into much detail on that. It's just something to be aware of, that once you start moving, then it can be a different coefficient of friction. That's why you often need to give something a shove to get it moving, and then it's actually a bit easier to keep it moving once it is. I'm not going to worry about that. As I said, normally I'll just tell you in any problems or scenarios, I would just tell you what the friction coefficient is, and that would be relevant to the scenario, whether it's at motion or at rest. So the actual friction experienced while moving is still going to be limited to that maximum friction force, although potentially with a different mu. But when an object is in motion, it's not limited to opposing forces anymore. It will experience the maximum friction force. It can, because the friction is trying to slow it down, it's trying to decelerate it. So if the object is in motion, then it will experience the maximum friction force. This means that you can actually have a friction force with no opposing force. So as before with the box on a slope, we saw a force down the slope, a parallel component of the weight force, and the friction force opposed that. If you didn't have that sideways component of the force, you wouldn't have the friction force, because the force from friction was just opposing the force that was trying to make the object move. But if the object's already moving, if the object is already moving, it doesn't need a force to keep it moving. That's Newton's first law. You don't need a force to keep it moving. It will remain in motion at a constant velocity in the absence of net external forces. So there's no force in the sideways direction if you have an object just sliding along a horizontal surface. But because it's sliding, if it's not frictionless, there will be a friction force, and that will oppose the motion, and then the object would slow down to a halt. So when an object is moving, it will just simply experience the maximum friction force. So that can all be quite confusing. I do understand that it is tricky to get your head around a lot of that. This is hopefully just going to sum everything up, but do spend some time just thinking about different scenarios, and obviously watching the next lesson where I do some worked examples. If the friction force is less than the push force, the object has net force in direction of the push and will accelerate that way. If the friction force is equal to the push force, the object has no net force parallel to the surface, and it will remain at constant velocity. And if the friction force is greater than the push force, then the object has net force opposite to velocity and will decelerate. Right, so that's the different scenarios that you can get while an object is moving. In a lot of cases, we're going to try and reduce friction. The gliders on the air tracks that you've seen in Lab 1, they use a little air cushion between the glider and the track, like an air hockey table, and that produces an air cushion which lifts the object off the surface, the glider off the track in this case. That means the two surfaces aren't actually rubbing together at all, so it doesn't matter how smooth or rough they are, they're not in contact, so we can't get friction from the surfaces rubbing. We can still get air resistance, we can still get drag, but we don't get the surface friction, which is what we're normally talking about with friction. Air resistance, we'll often call it air resistance to differentiate it, but it is a form of friction. Sometimes you'll see it just referred to as drag as well. So unlike surface friction, drag gets bigger as an object speeds up. So surface friction, there's a maximum force given by mu times the normal force. That's the maximum it can get to. For air resistance, it doesn't have a maximum. It just depends on the velocity of the object through the air, because air resistance is essentially pushing that air out of the way. If you've got a car driving down a road, it's got to push air out of the way in order to be where that air used to be. It's got to push the air out of the way. The faster it goes, the more air it just constantly has to push out of the way, and that means it needs more and more force to do that. So there's more and more air resistance as you get faster and faster. So there's no limit in the same way that we have for surface friction. We're actually now going to go back to the rate of acceleration due to gravity. When we had no other forces acting on an object, things fell with an acceleration of g, 9.81, or here in New Zealand, closer to 9.80 meters per second. As soon as you bring in air resistance, then you need to start thinking about how that acceleration is going to change. Remember that the acceleration of 9.8 is only when the only force on an object is the force due to gravity, the weight force of the object. As soon as you have some air resistance, so as soon as you're traveling through air, which you always are if you're falling towards Earth, as soon as you're traveling through air and pushing it out of the way, you're going to have air resistance, which is going to create an opposing force. And since your motion will be directly downwards, because that's what gravity does, it makes us fall directly downwards, this air resistance would be directly upwards. And so it would cancel out some of your weight force, and you would accelerate more slowly after you start to speed up. So that means right at the very start, before you're even moving, you're going to have an acceleration. So that first instant, you're going to have acceleration of 9.8 meters per second downwards. As soon as you start accelerating downwards, then you're going to actually lose some acceleration because you're gaining this drag force. And that means that as you get faster and faster, the air resistance is going to get bigger and bigger, and your acceleration is actually going to get less and less. At a certain speed, you're going to be going fast enough that the force needed to push the air out of your way is the same as the force that the Earth is exerting on you, and therefore you will have no net force, no acceleration, and your velocity will not change. And this is known as terminal velocity. So terminal velocity is just when the weight force of Earth pulling you down is equal to the resistance force of the air pushing you back up or trying to slow you down. Obviously, it's not going to push you up, but it will slow you down, which results in an upwards force. For a human, face down, if you spread your arms and legs out, so you go spread-eagled, straight down, then that terminal velocity is going to be around about 200 kilometers an hour. If you pull your arms and legs in and make yourself more aerodynamic, then you can get up to 320 kilometers an hour. So those are the top speeds of skydivers when they're falling through the air. The next part is on tension. So tension is almost a special case of normal or support force where we're trying to keep something from falling downwards. So we're all familiar with hanging an object to support it. Imagine hanging an object directly off a hook in the ceiling. So here the black hanger thing is our object and the brass hook is the one on the ceiling. When you hang that object on, you've got a single interaction with a single pair of forces. You can see I've drawn the two little blue arrows to represent the forces. We've got the support force onto the black hanger from the brass hook, and that is upwards, so it's counteracting the weight force on the hanger. And then you've also got the push downwards force from the hanger onto the brass hook. And those are going to be equal and opposite by Newton's third law, and that is what is stopping the mass, the black hanger, from falling downwards. So that's easy enough. If you just hang something directly from this hook, hopefully you're all happy with the idea of the forces involved there. But what happens if you instead use a string to hang the object off the hook? You're still getting a force exerted onto the hanger to stop it falling down. That's the whole point of hanging something. You must have a force onto that hook that is preventing it from accelerating downwards. And that force must still be coming from the hook attached to the ceiling, because that's the only thing it's attached to. But we've got the string in the middle that is somehow transmitting that force along its length. And indeed, that's exactly what it's doing. Tension is transmitted force. So the idea is the weight of that object is being transmitted from the object to the hook that's supporting it via the string. So if the object has a weight of 10 newtons, the string will have a tension of 10 newtons. If it weren't 10 newtons, then it would not be enough to balance the object's weight force, and the object would be accelerating, not at rest. So the tension in the string is always just going to be the equal to the weight force of what it's supporting. One of the problems we're going to look at in lesson 10 in the next lesson is going to deal a little bit more with tension, and it's actually going to introduce pulleys, which I haven't talked about in this lecture, but we'll talk about those in that lesson. Thinking about the force pairs, rather than just having that one force pair that we had when we hung the object directly on the hook, we now have two force pairs. We've got the object with the end of the string and the other end of the string with the hook. All four forces are the same magnitude. They have to be, because the string is at rest, and there's only two forces acting on the string. Assuming the string's mass is negligible, which is something that we will often make the assumption of, where we're not actually saying it's negligible, but we're saying it's so small compared to the masses of the object that we don't care about it. So assuming that the mass is negligible, then it means that the string only has those two forces on it, the one from the hook onto one end and the one from the object onto the other end, and they must be equal and opposite. In reality, with a string that does have some mass, the one with the object would be slightly different from the one at the top, because you've also got this weight force to account for. But usually that's so tiny compared to the object, we can ignore it. And so if those two forces weren't the same, then the string would be accelerating. And the string clearly is not going to be accelerating, so that means those two forces acting on the string must be equal and opposite. And because they are one part each of those two force pairs, that means all four force vectors must be the same magnitude. Two of them will be pointing up, two of them will be pointing down. So again, just thinking about the force pairs, thinking about what's interacting with what, usually will be enough to figure out what these tension forces are going to be. And finally, we're introducing a new concept here, which is Hooke's law. So far, every object we've looked at, we've just treated as if it's perfectly rigid. It can't be bent or squashed or compressed or stretched in any way. But of course, there are things that can be squashed and stretched and compressed. And we are talking about springs. So we're all familiar with springs. If you compress a spring, it will try to uncompress itself. It will push back against you as you're squashing it. And that should be no surprise given Newton's third law. And if you stretch it, it will try and unstretch, so it will pull on you as you pull on it. So again, Newton's third law should not be surprising there. So those are springs, but what sort of forces are involved? Hooke's law tells us the magnitude of the force needed to change the length of a spring by some amount x. There is this other letter in there, k. K is a property of each spring. So if you are given a spring, you need to know its K. You can either determine it by measuring F and X and figuring out K, but often we'll just tell you what K is, and then we can figure out the force needed for certain changes in length. So K is a property of the spring. We call it the spring constant of the spring. Spring constants can apply to things other than actual springs, but for simplicity, we tend to just keep talking about springs. So the bigger K is, the stiffer the spring is, the thicker, tougher the spring is, and the more force you will need to make a change in displacement. The smaller K is, the weaker and thinner that spring is going to be, and the easier it is to change that length. Spring constant K has units of newtons per meter. Try and figure out the dimensions of K is a good little exercise. I'm not going to do that, but I do thoroughly recommend you have a go at that. Just remember what the dimensions are for newtons, and then you've got the dimensions for meters or length on the bottom as well. So do try and figure that out. Spring constant K, as you can see from the equation, hopefully it's no surprise that it's newtons per meter, because we've got F equals Kx. If X is newtons and X is meters, the only way this equation balances, the only way the units are the same on both sides of the equation is if K has units of N, newtons, to equal the force on the other side, over meters to cancel out the meters from the X. So the units have to be newtons per meter. The other thing that's a common problem with Hooke's law is the idea of plus or minus Kx. So sometimes you'll see it written as F equals Kx, other times you'll see it written as F equals negative Kx. So which is correct? Unfortunately, both are. Both are correct because it depends on whether we are talking about the spring as our system or the objects attached to the spring as our system, or indeed the whole thing as our system. The negative is sometimes included by people who want a reminder that the spring exerts a force in the opposite direction to its change in length. But hopefully you all know that. You all know that if you stretch a spring and it's got longer, then obviously it's going to try and get shorter. It's going to pull itself back to where it should, its original length. Hopefully you all can see that without having to be told. If you stretch a spring, it's going to try and make itself back to its original length, which means it's trying to get shorter, which is in opposition to the way you pulled it to start with. And if you squash a spring, it's going to try and get longer, which is in opposition to that change in length again. So that negative is sometimes included as a reminder of that, but personally I feel like that's a bit unnecessary for anyone that even knows at a basic level what a spring is. But the plus and minus aren't always relevant, because if you are talking about the force that you need to apply to the spring to compress it, then that force is going to be in the same direction as the change in length. If you push a spring this way, its length is going to get shorter. If you pull it that way, it's going to get longer. So the force is in the same direction if you're talking about the force that you have to apply to the spring. By Newton's third law, obviously, the force of the spring back on you is going to be equal and opposite. So again, the positive and negatives in those equations aren't always reliable. If you just rely on maths, then you can't always figure out the correct directions of the forces. So the key is to remember that F equals kx will always tell us the magnitude of both forces in the interaction pair. That's by Newton's third law, they're going to be the same magnitude, they're just going to be opposite directions. So use F equals kx and figure out the magnitude of the force. That's perfectly fine. That will always be the magnitude. And then you can figure out the direction of the force, independent of the magnitude. So it doesn't actually matter whether you do the force and then the magnitude, the magnitude and then the direction, or other way around. The point is, figure them out as two separate things. Use F equals kx to get the magnitude of the force and think about the scenario. Do the physics to figure out the direction of the force. Is the spring being compressed and will it push back? And what's your system? That's the important step at the end there that a lot of people forget when they're talking about springs. What's the system? So the spring, if the spring is our system, then the force is on the spring. Right? The force on the spring is from the person who's compressing it, and it's going to be in the direction of the compression or in the direction of the stretching. If the system is the thing that's doing the compressing, then the force is from the spring and it's going to be opposing that change in length. So the direction, you have to think about the physics of the system. So that's the end of this lesson. I realize that was quite a lot to get through, but we've already hinted at quite a few of these different forces, and hopefully this lesson has been enough to help you understand what they are. As I said already, in the next lesson, I will essentially, sorry, just trying to cancel the screen sharing thing. In the next lesson, I will talk through a few different problems. That's all I'm going to do. The whole lesson is just going to take what we've looked at in these first few lessons. So what are forces, what are the Newton's laws, and what are these common forces? And we're going to look at a few problems and just work right through them.